Okay, Kepler's laws were developed, obviously, by Kepler to explain planetary motion, and he had three of them. We're going to focus mostly on the third one for right now. We'll get back to the first and the second when we get to angular momentum in a couple of weeks. So all you really need to know right now are just what the three laws are, specifically the first and the second, and then we'll be using the third law. So his first law tells us that each planet moves about the sun in the path of an ellipse, and the sun's at one focus. So what that means is that it is not a circle, but it's this ellipse shape, and the focus would be the sun at one and then the planet at the other. I'm sorry, not the planet, but another focus somewhere else, and then the orbit would be elliptical. Some planets have more elliptical orbits than others. They're mostly circular, but again, they're not exactly circles. So all the first law tells us is that the path of a planet is an ellipse. Kepler's second law tells us that, and this is what we'll focus on when we get to angular momentum, each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal periods of time. So all that tells us is that when a planet is closer to the sun, it's going to move faster than when it's farther from the sun. And again, that has to do with several factors that we'll talk about later, but equal areas, so that means that the area between C and D is the same as the area between A and B in equal amounts of time. So it'll take shorter to travel this longer distance than it would to travel this smaller distance. And then Kepler's third law, the one that we will be focusing on, tells us that the ratio of the squares of the periods of any two planets revolving around the sun is equal to the ratio of the cubes of their distances from the sun. So that sounds complicated, it's really not. So the ratio of the squares of the periods of any two planets. So that means TA over TB squared, and A and B just refer to planet 1, planet 2, is equal to the ratio of the cubes of their distances from the sun. So this equals RA over RB cubed. That's it. So Kepler's third law tells us this ratio. You might also see somewhere, so let me just say what these are. So TA and TB, these are the periods. RA and RB are the distances from the sun, or whatever object they're orbiting around. You might see, instead of RA and RB, you might also see the letter A instead of R. Just be aware that A and R are the same thing. So A is usually used with Kepler's laws, but for simplicity's sake, we'll keep it with R. Kepler's third law is also directly related to circular motion and universal gravitation, and we are able to derive what the period of an object is as it's orbiting around the sun. So if we know that an object is orbiting, and we know that as it's orbiting, the speed is equal to 2 pi times the radius over the period, and that the only force acting on them would be the force of universal gravitation, then we know that mv squared over r would equal g m1 m2 over r squared. And this mass right here is for the centripetal force of the object that's orbiting, so that's going to be your smaller mass. I'm just going to call that m1. M1 appears on both sides, so that goes away. This R goes away, and that just becomes 1. So we're left with, and we've seen this already, V squared equals G M2 2 over R. Okay, making a small substitution. I'm just going to move this. We know that V, and this is the same V right here, equals 2 pi r over t. So V squared equals 2 squared is 4, pi squared r squared over t squared. So I'm going to substitute this in for this to get 4 pi squared r squared over t squared equaling g m2 over r. Okay, so I'm going to isolate t squared. T squared equals 4 pi squared r cubed over g m2. And m2 again refers to the mass of the more massive object or whatever's being orbited. So t is period. And period needs to be measured in days. Seconds. So period, the units need to be seconds. You have 4 pi squared, those are both constants. Your r is the distance, and that's measured in meters. And then your m2 is the mass of the more massive object, and that's measured in kilograms. So you need to make sure that whenever you're given the period or the radius that you have those distances in seconds and meters. That's not the same case for up here. As long as these two and these two are in the same unit, because they're ratios. If they're in the same unit as each other, then it's fine. It doesn't have to be seconds or meters. It can be days, it can be kilometers, light years, whatever. But down here, with this mathematical equation, it does matter whether or not you're doing seconds, days, whatever. So make sure that this period is in seconds, this radius is in meters, and mass is usually in kilograms. Okay, so let's do some examples. Okay, the asteroid Icarus, though only a few hundred meters across, orbits the sun like the other planets. Its period is 401 days. What is its mean distance from the sun? Given. Tells us that the period is 401 days. And we know that the mass of the sun is 2 times 10 to the 30th kilograms. And we are looking for radius, distance. So given a period and a mass, looking for the distance, we're going to use Kepler's third law. T squared equals 4 pi squared r cubed over gm. Rearranging this to solve for r, we get t squared gm over 4 pi squared equals r cubed. We need t in in seconds. So converting days to seconds, you're going to do 401 days times 24 hours in 1 day times 3,600 seconds in 1 hour. So this in seconds is equal to 346,400 seconds. Okay, so now we just have to put the numbers in. So we get 364,400 seconds squared times g times 2 times 10 to the 30th kilograms over 4 pi squared, I'm out of room, that equals r cubed. This number should come out to 4.05 times 10 to the 33 meters cubed equaling r cubed. Taking the cube root of r, so in your calculator just hit math 3, and that'll take the cube root of the number. 1.59 keeps on going, times 10 to the 11th meters equals r. So the distance is about 1.60 times 10 to the 11th meters. Okay, I'm gonna skip number 2. We'll do that as a warm-up in class. I want to scroll down to the first practice, and that way we can just use the other version of Kepler's third law with the ratios. So it tells us that Neptune is an average distance of 4.5 times 10 to the 9th kilometers from the sun, and we want to estimate the length of the Neptunian year, given that the Earth is 1.5 times 10 to the 8th kilometers from the sun on average. So listing what we know. The radius of Neptune is 4.5 times 10 to the 9th kilometers. The radius of the Earth is 1.5 times 10 to the 8th kilometers. And when I say radius, I'm talking about distance, radius of orbit. We know that the period for the Earth is 1 year, and we're looking for the period of Neptune. So Kepler's third law, T Neptune over T Earth squared will equal distance for Neptune over distance of Earth cubed. We're looking for Tn, so just rearranging this. We get period for Neptune squared equals radius of Neptune over radius for Earth cubed times the period for Earth squared. So just algebra cross multiplying. So this will equal 4.5 times 10 to the 9th meters over 1.5, this is kilometers, not meters, times 10 to the 8th kilometers, all of that cubed, times 1 year squared. Kilometers will cancel, put this in your calculator. We should end up with Neptune's period squared equals 27,000 years squared. Taking the square root, we should get 164.31, keeps on going years. So it takes Neptune approximately 160 years to orbit the sun. So again, just a simple ratio. The units don't matter as long as the units are the same with what you're dividing. So these were both in years, these were both in kilometers, and then we just had to solve. We'll do more practice in class tomorrow, but that's about the extent of Newton's third law. There's not really much past that. And again, first and second law, you just need to know what they are. We'll do more applications with them once we get to rotational motion.